Okay, good evening to all, and welcome to the another session of the NPTEL course Heat Transfer. So this is our fourth session. So today we will be discussing about the week four topics, which was the fundamentals of convection. So I will just give a brief overview about the week four topics. So the introduction to convection was the main topic for week four. So where the convective heat transfer coefficient, Nusselt number, etc. was discussed. Then the equation of state for non-isothermal systems were derived, where we will be taking an elemental volume dx, dy, and dz, and we will be equating the energy, or we will be writing the energy balance equation to find out the energy equation of for that system. So this was the major topics covered in week four, and today we will be discussing some simple questions, practice questions based on this week four topics. Okay, let's get started with the first question. So it's a very simple question. So it's a coolant fluid at 30 degrees Celsius flows over a heated flat plate maintained at constant temperature of 100 degrees Celsius. So the boundary layer temperature distribution on the plate may be taken as this expression. So this is the temperature profile for the uh, temperature profile within the boundary layer. So the thermal conductivity of the fluid and all is given. So we have to find out what is the heat transfer coefficient at at the location, or at the location means at the location where this temperature distribution is specified. Okay, so uh, so you can start trying. I will just draw the schematic. It is just a flow over a flat plate. So this is the flat plate. So over which the flow occurs. So this is flow is there. So so the temperature of the flow T infinity is given as 30 degrees Celsius, and the Ts is, that is the temperature of the surface or the plate, is given as 100 degrees Celsius. So as there is a temperature difference, there will be heat transfer taking place. So I'm not as you know, as it's a flow, both the thermal boundary layer and also the velocity boundary layer will grow over the plate. So if there is no heat transfer, there will not be any thermal boundary layer. But even though there will be, as it is a flow, velocity boundary layer will be formed. So now we are more concerned about the heat transfer point of view. So, and also the temperature distribution is given. So I will be drawing only the thermal boundary layer. So this is the thermal boundary layer. Okay. So uh, so the thermal boundary layer will be approximately like this. It's an exponential decay. Here's the free stream. So So this temperature profile with respect to y is given. So we are asked to find out what is the heat transfer coefficient. So I can try this out. So it's just an equation, means equating the both convection and conduction. So have we got the answer? Okay. We know already that this is the convective heat transfer coefficient H. So minus K dt by dy at y is equal to 0 should be equal to H E S minus T infinity. So this is the energy balance. Okay. So what is H? Minus K dt by dy at y is equal to 0 divided by Ts minus T infinity. So K is, so first we have to find out what is dt divided by dy, right? So this is, it is d by dy of 30 plus 70 e raised to minus y. So it becomes minus 70 e raised to minus y, right? At y is equal to 0 means it becomes minus 70. Okay. So just substitute this value. H is given as 1. So k is given as 1. So minus 1 into dt by dy is at y is equal to 0 is minus 7. Sorry, minus 17 divided by ts is 100. T infinity is 30. So it's 70 by 70, which is 1 watts per meter square Kelvin is the heat transfer coefficient at the location where this temperature profile is specified. So the answer to this question is 1. So I hope there may not be any doubt in this question, because as to start with, I have taken a very simple question. It's just equating the conduction. As we know, this first layer of fluid that is in contact with the boundary or the solid surface will be at stagnant or will be stationary. So the flow, so the heat only can transfer through conduction through that fluid there. So that heat has to be transferred to the flow of to the fluid which is at the free state. So whatever heat that is transferred by conduction, it should be conducted away to the fluid. We just equated that formula and we got the heat transfer value of heat transfer coefficient as 1 watts per meter cube. Okay. So let's go on to the next question. So it's a question based on our energy equation that's already discussed in the class. A similar kind of question is also discussed. So I have once more taken a similar kind of question to just to make more clarity. So it's an oil. So oil flow in a general bearing can be treated as a parallel flow between two large isothermal plates with one moving at a constant velocity of 12 meters per second and another stationary. Okay. Consider such a flow with a uniform spacing of 0.7 mm between the plates. The temperature of the upper and the lower plates are also specified. We have to find out the velocity and temperature profile. So the actual situation is we have a bearing, and within which one shaft or any one shaft is rotating. Okay. So in between this, we have the lubricant. That is the lubricant oil. Oil is filled in between the bearing and the shaft, so that metal to metal contact will not occur and the wear and tear can be reduced. So this is the practical situation. So this we can approximate it as a flow between a parallel plates, because the thickness of this oil film or the clearance will be very less. So as you say, it's only 0.7 mm. So we can consider it as a flow over a flat plate. So say for example in this question, directly the velocity of the so the velocity is given. Okay. So but in some cases the maybe the omega or the RPM of the the bearing or the shaft will be given. That is n will be given. In some cases, in some questions can be also given. So we know the omega is equal to 2 pi n by 60. So we can take this this velocity as v is equal to r omega. Right. The radius of the shaft will be also given. So without directly giving this constant velocity, the questions can be asked like this also. So, but in this question, directly the velocity of the plate is given. So we are approximating that situation as a flow over a flat plate. Sorry, the flow between two parallel plates. Okay. So this plate is moving with the velocity is given as 12 meters per second. Okay. So this plate is stationary. And the height, I'm not taking the values now. So I am deriving it in general terms so that at last you can substitute the values. So this I am taking it as L. That is the L or X. You can take any nomenclature. This I am taking as ds1 and this is ds2. Okay, and the velocity as v. So, and this is the coordinate system I am taking xy, and the flow takes place in x direction. Okay, so this is a we can approximate this as a 2D system as as we are assuming that the z direction is very large, so that there is no variation along its direction. So we can approximate this as a 2D case, and also as it is a flow between parallel plates, we can there will not be any v component of velocity. So the v component of velocity, that is x component of velocity, I am taking it as u, and y component of velocity I am taking it as v. Okay, so the v is 0. So from the continuity equation, if we take continuity equation, dou u by dou x plus dou v by dou y should be equal to 0. So this is 0. So which implies dou u by dou x should be equal to 0, which implies u is a function of x or y. U is a function of x or y. U is a function of, as the derivative of a derivative with respect to a variable is 0, then that function, that variable or that value, that this u is not a function of x. Either it can be 0, or it can be a constant, or it can be a function of some other values. So as it is a 2D case, we will write u is a function of y in general. Okay, so we have the two boundary conditions here. So here v is equal to 0, right? So at x, at y is equal to 0. Sorry, so we can write this as no. We have to find out the velocity profile to apply the boundary conditions. So we get u is a function of y only. There is no dependence on x. Next, I'm writing the x momentum equation. X momentum equation for a 2D case. Okay. So rho times dou u by dou t plus u dou u by dou x plus v dou u by dou y is equal to minus dou p by dou x plus rho gx plus mu times dou square u by dou x square plus dou square u by dou y square. So this is the general two-dimensional momentum equation. So now we are going to apply the assumption. Sorry, our condition. It's a steady state. So this term becomes 0. So as u is 0, this is also will become 0. Dou u by dou x is equal to 0. So this term will also be 0. So we are neglecting the effect of gravity. So this also becomes 0. Neglecting gravity. And there is no imposed pressure gradient. So it is generally known as a viscous or a shear driven flow. Okay. So there is no applied pressure gradient. So dou p by dou x is also 0. The flow is happening because of the movement of top plate. And dou u by dou x is also 0. So the remaining, what is the remaining term? Remaining term is mu times dou square. So we can write, so we can convert this partial derivative into the ordinary derivative, as u is only function of y. So mu d square y by dy square is equal to 0. Right. So if we integrate this, you will get u of y is equal to c1 y plus c2. This is the velocity profile. It's a linear velocity profile we are getting. So now we are applying the boundary conditions. Right. y is equal to 0. What is u? The plate is stationary. So u is 0. So C2 becomes 0. At y is equal to L, u is equal to v. Okay. So v is equal to C1 times L. So we will get C1 is equal to v by L. So we can write what is the velocity profile. It is u is equal to v by L times y. So this is the velocity profile. So we get a linear velocity profile. Okay. So the first part of our question is completed. So we found out the velocity profile. Next we need to find out what is the temperature profile. Okay. So for temperature profile also, what we need to say, the temperature, as these two temperatures will be as two plates will be at different uh, temperatures, there will be a temperature gradient happening, right? So we have to find out what is the temperature profile. So the plates are isothermal, and there is no, the plates are isothermal means at any location the temperature of the plates will be same. That is mean when plates are isothermal and there is no change in the flow direction, and also the flow is taking place in x direction. We can take temperature as a function of y only. Okay. So the temperature is not a function of x. So now we are writing the energy equation in 2D case. Okay. So rho Cp dou T divided dou plus u dou T by dou x plus v dou T divided by dou y is equal to k dou square T by dou x square plus dou square T by dou y square plus mu times I. Okay. So now I will ask one question. So in the class it is specified, it is so in this original equation we have to so in general expression, general energy expression, there will be a viscous displacement term. This is the viscous displacement term. So whether in this situation or in this question, we need to apply or we need to consider this viscous displacement term or not. So in the lectures are discussed where we can neglect the viscous displacement terms and where we need to use or we need to add the viscous displacement term in the energy equation. So what are the I think two situations are as mentioned where we need to consider the viscous displacement. Can you just remember what are the situations where we need to take or we need to consider this viscous displacement terms? One is when the fluid is of high viscosity. Okay. Another is when the fluid is at high speed or the velocity, high speed flows. Both satisfies here because oil, we know it's of a oil, the viscosity of oil is comparatively very high, and also the speed velocity is also very high. It's almost 12 meters per second. So in these conditions, like flow over channel bearings and all, we need to consider this viscous displacement terms. So what is phi? So phi is the expression for phi is 2 times dou u by dou x the whole square plus dou u by dou y the whole square plus dou u by dou y plus dou v by dou y, dou u by dou y plus dou v by dou x the whole square. So this is the energy equation. So now we will cancel out the terms. It's a steady state, so this is 0. So temperature, so V is 0. Temperature is function of Y only, so dot T by dot X is 0. And this term, dot T by dot square T by dot X square is also 0. And if you come to this, be where deriving about the velocity, this is 0, that is dou U by dou X is 0. V, there is no, assume that there is no V component of velocity. So dou V by dou also 0. Dou V by dou X is also 0. So the remaining terms is 0 is equal to A d square T by dy square plus mu times du by dy the whole square. So this is the equation we will get. Okay, after simplification. So next, what is we have to find out. Now just integrating it and say giving the boundary conditions, we will get the temperature profile. Okay, so d square T by dy square is equal to minus k, sorry, mu by k dy by du by dy the whole square. We all, what is du by dy? It is v by l, right? So we already found out. So this is equal to minus mu v square by k l square. So if you means integrate it twice, we will get t of y is equal to minus mu v square divided by 2kl square y square plus c1 y plus c2. Okay, this will be the temperature profile. Next, just we need to find out what means give the temperature boundary conditions at y is equal to 0, t is equal to ts1. So ts1 is equal to c2, and at y is equal to l, t is equal to ts2. That is ts2 is equal to minus mu v square divided by 2k. This l square, this y square and l square will get cancelled, plus c1l plus ts2. Okay. So from this we will get c1 as ts2 minus ts1 by l plus taking this l square by 2kl. Okay, this is the c1. So if you substitute this, we will get the temperature T as I just some rearrangement is required. So because of space constraint, I'm writing the final expression. So when you put this C1 and C2, yeah, both expressions are correct. So if you put C1 and C2 into this expression, you will get the final expression as mu v square by 2kl square yl minus y square plus t2 minus t1, sorry, ts2 minus ts1 by l plus ts1. This will be the final expression you will be getting. So as you say, see, the temperature is a quadratic function of y, but the velocity is a linear function of y. So the answer to this question is velocity is linear and the temperature is quadratic function. So this type of question you can expect in your normal descriptive examination. So and also a small part of this can come in the a small part of these questions can be split up and form questions in GATE and ESS also. So I hope this how this temperature profile and velocity profile are derived for this question. Next, it's a continuation of questions. So now we are going to substitute these values. So we need to find out what is the maximum temperature and location where it is occurring. So we got the temperature profile. What is the temperature profile? T is equal to mu v square divided by 2kl square yl minus y square plus ts2 minus ts1 by l plus ts1. So this is the expression for temperature at any y location. Okay. So we need to find out the maximum temperature and where it occurs. So we are differentiating this with respect to y. Okay. If you differentiate this with respect to y, what you will get is L minus 2y, and these terms will be constants. And to get the silent point, that is y, which this that is where the gradient becomes 0. So the gradient will become maximum. We have to equate this. We have to equate this dt by dy is equal to 0. That's it. Sorry, here it is 1y is there. This I missed it. 1y is there. Okay. So it becomes ts2 minus ts1 by n should be equal to 0. So now we have to find out what is y. So mu v square divided by 2kl square l minus 2y is equal to minus of ts2 minus ts1 by l. So mu v square by 2kl minus mu v square by y by 2kl square is equal to minus ts2 minus ts1 by l. Okay. So now we have to find out what is y. So y is equal to mu v square by 2kl plus ts2 minus ts1 by l. We are multiplying it with l square divided by 2kl square by mu v square. Okay. So if you do it, you will get sorry this 2 it's not there. So if you multiply it, you will get this cancel. Well, L square 1, this becomes L by 2 plus ts2 minus ts1 k L by mu v square. Okay. You will get y is equal to L times half plus ts2 minus ts1 k divided by mu v square. Okay. I hope this is clear to you. So now it's just we need to substitute this value. So one more thing we can try. You can put this you can differentiate this once more. Okay. So if you differentiate d square t divided by dy square, just to confirm whether it is maximum or a minimum one. So if you again differentiate it, it becomes minus 2. So this is gone. So minus 2 mu v square divided by 2kl square. Okay. So we need not substitute any value of y. So all the values, that is mu, v, k, l, all are positive. We cannot have. So all these v square, l square, mu, k, all are positive. So we cannot have a negative value for this. But there is one negative side instead. So as the derivative is negative, so this will be a maximum point. So just for checking, you can do this. Okay. Just this is the location. This is the y max location. Okay. So just substitute this value. Substitute the values. What is L? So L is 0.7 mm, 0.7 into 10 raised to minus 3, half plus TS1 is 40 minus 15. Okay. So here the temperature, so sorry. So I think I forgot to give this K mu value of this oil. So you can take at average temperature because one is at 40 degree and one is at 15 degrees. So usually what we do is when the two surfaces are at say for example as a two different temperatures, we will take the film temperature or the average temperature. So what is so I'm taking the giving the temperature property set 40 plus 15 by 2, which is 27.5. So it will be normally given in the question. So take K is equal to 0.145 watts per meter Kelvin and mu is equal to 0.580 Newton seconds per meter square. Okay. So substitute these values. K is 0.145, mu is 0.580 into V square whole square. So you can do the math later. So it will come out to be around y is equal to 0.38 mm. So that is means one thing we have to consider is we all derive by keeping the fact that I'm measuring y from the bottom plate. So you can measure y from top plate. You can take your own nomenclature, or you can set the coordinate as your wish. But the actually the expression will be almost similar, but it will be some difference will be there based on how you select the y value or how you select the coordinates. But the final answer will be same if you do in any coordinate or if you give any value. So I am taking y from the bottom plate. You can consider this as okay, if this make get confused. This is my axis. Okay. So you can take this middle as axis also. So then you have to give the boundary condition. So while selecting this coordinate system, you have to take care that we have to simplify it at easily. So if you give so if I in this case I have given bottom plate as y is equal to 0. So this first one constant becomes already 0. So so the choice of coordinate axis, you should choose the coordinates in such a way that it will help you to solve the question. Okay, you can take this middle as middle of this plate, that is L by 2 at L by 2 as your coordinate system also. So then what will be the boundary condition? At lower plate will be at minus L by 2 and upper plate will be at plus L by 2. So the C1 will not be 0. So the C1 and C2 values will be 0. But when you put the values, or so when you put the values at these two plates or these two uh, uh, plates, at both the approaches, the result will be same. So you should be careful in taking the coordinate. Okay, so from the bottom plate, at a distance of 0.38 mm, we have the maximum temperature location. So next we want to find out what is Tmax. Just substitute the y value at this expression. Okay, that is T. So sorry, what is this expression? Mu v square divided by 2k L square yl minus y square plus ts2 minus ts1 by L y plus ts1 at this at y is equal to 0.38. You can just substitute these values. So everything is given mu v k l y we have to substitute 0.38 mm, L we have to substitute 0.7 mm. So be careful about the units. You use whatever units you convenient. So better to convert it to meter. Okay. So uh, so if you substitute all these values, you will get the T max as around 100.04 degrees Celsius. So so one of the interesting thing you I think you noticed here is you can notice is one plate is 14 degrees Celsius and another plate is at 15 degrees Celsius. But the temperature, the maximum temperature that is building up in between these two plates is 100 degrees Celsius. Okay, which is almost more than twice that of the maximum temperature plate. So this is because of the mainly because of the viscous dissipation, heat generated due to viscous heat dissipation. Okay. So, so the more about this is discussed by Star in the lectures. So you can refer to the lectures for more details. So next, also the same part, same question. Last part, we have to determine the heat flux from the oil to each plate. Okay. So this is this this is top plate, that is TS2, TS1. This is I am considering it as QO, Q and QI from oil to plate. Okay. And this is my coordinate axis. X, Y. So it just direct substitution. We know QI is equal to minus K dt by dy at y is equal to 0. Okay. What is minus K dt by dy at y is equal to 0? Dt by dy already I know at y is equal to 0 means this part becomes 0. So it becomes mu v square divided by 2kl plus ts2 minus ts1 by l. Okay. So if you substitute, I'm not substituting these values. If you substitute these values, you will get it as around 64835.71 watts per meter square. Okay. So this you can try this at home, your home. You can just substitute these values. So you will get minus. Okay. So 64.835 kilowatts per meter square. Now Q, that is, this is Q upper plate. This Q up, sorry, Q lower. I am changing it as this is Q lower and Q upper. Okay, Q lower plate and Q upper plate also same, minus K dt divided by dy at y is equal to, that is L. So if you substitute to this equation, that is y is equal to L. Y is equal to L means you will get minus K minus mu VL square divided by 2KL. That is y minus 2y. Sorry, L minus 2y. So L minus 2L is minus L. Okay. Plus TS2 minus TS1 by L. So you will get the answer as 5.45 kilowatts per meter. So this you can I think you can just it's a direct substitution of the values. You can try this at home. So the answer is Q lower is 64.83 and Q upper is it's not it is 54.5 kilowatts per minute. So the answer is okay. So if this both, so if you can see that the heat fluxes are different. So if you take the same, if you take the uh, temperature of the upper plate and lower plate as same, then the the difference that is going to happen mainly is the y max will be at the y max will be at L by 2. That is the middle distance, and also the heat flux will be values of heat fluxes will be same. So to that you can try means I'm giving this as an example exercise to you. The same question you take, the same question you take and put and take both the temperatures are same, that is TS1 and TS2 are same, and find out. And find out what will be what where the maximum temperature happens. That is the location of Y max, and also you calculate the uh, heat flux of lower and upper plates. Okay, that's I'm leaving it to as an exercise. So next is just we will have a small discussion on some general concepts. Does the Prandtl number depends on type of flow? Can you answer? Just true or false? That's enough. Okay. So actually, what is Prandtl number? The Prandtl number, by definition, it is the ratio of momentum diffusivity by thermal diffusivity. Or if you write in terms of formula, it is mu by alpha. Mu is the momentum diffusivity divided by thermal diffusivity. Okay. So what is alpha? Mu. Mu is, we can, in other terms, we can write mu is, sorry, this is kinematic viscosity, and this is this is kinematic viscosity, or we will normally call it as momentum diffusivity. Alpha is thermal diffusivity. This is mu by rho, and alpha is rho Cp by K. So mu Cp by K. This is another expression for Prandtl. Okay. So it is the actually the relative effectiveness of effectiveness of momentum and energy transport by diffusion. Okay, it is the measure of actually it's a measure of relative effectiveness of momentum and energy transport by diffusion in velocity and thermal boundary layer. Okay, that is the physical significance of Prandtl number. So it also gives a measure of uh, relative thickness of the thermal and velocity boundary layers. Okay, so I will just show you how it is related. So I am having a I am having three situations. This is a plate. Okay, so this is thermal boundary layer. This blue one. and this is hydrodynamic boundary layer. This is thermal boundary layer, and this is hydrodynamic boundary layer, and both thermal boundary layer and hydrodynamic boundary layer coincide. So if you are given a situation like this, say for example in any examination, so you are given a graph, or you are given a situation like this, you are asked to find out, you are asked to choose between or match between three options. That is Prandtl number less than 1, Prandtl number greater than 1, Prandtl number is equal to 1. Okay. So you see, in first case, in case 1, in case 1, you can see that the momentum disturbance travels at a greater distance than the thermal disturbance, right? So actually, this boundary layer is the area, or it's a distance where this change in the velocity or change in the temperature happens from, if it is velocity, it's from 0 to free stream velocity, and if it is terms of temperature, it is from temperature of the plate to the free stream temperature. So if you see the first case, the momentum travels faster than heat. Okay. So by this definition, can you suggest what will be the Prandtl number value? So this numerator term, the momentum diffusivity, the momentum transfer rate is more as compared to the thermal transport rate. So in the first case, the Prandtl number will be greater than 1. Okay. In second case, it will be simple. You can see the heat transfers, or the rate, or the heat travels, or the heat thermal disturbance travels more than the momentum disturbance. Okay. So the denominator is greater than the numerator. So here the Prandtl number will be less than 1. So in the first and in the third case, both are same. So the Prandtl number will be equal to 1. So this is how, if you give, so for example, you are given a situation like Prandtl number is greater than 1, and you are asked to interpret what will be the boundary layer and thermal boundary layer and velocity boundary layer, or how the thermal boundary layer, and you are asked to draw the thermal and velocity boundary layer. So you can just think, if Prandtl number greater than 1, the Prandtl number is greater than 1. So the momentum transfers more, the momentum travels more. The rate of momentum transfer will be greater than the energy transfer. So the thermal boundary layer, velocity boundary layer will be more than thermal boundary layer. So we will discuss this in detail, I hope, in the coming classes. So just for giving some examples, so when a Prandtl number is very much less than 1, it's liquid metals. Basically, it's liquid metals. The Prandtl number is, for liquid metals, Prandtl number is very much less than 1. So the velocity boundary layer will be very thin as compared to the thermal boundary layer in case of liquid metals. And another case is oil or lubricants, where the Prandtl number is very much greater than 1. Here, the thermal boundary layer will be very small, and the momentum or the velocity boundary layer will be very large. So just some common Prandtl number values of air is 0.7, and for water, it's like is almost 6.9 to 7 at 25 degrees. Okay. So just have an idea about the Prandtl number of commonly used fluids like air and water. No, because sometimes it may not be given in the question. So please know Please be familiarized with the Prandtl number values of water and air. Okay. So the next question is in the expression of Nusselt number, the thermal conductivity of solid should be used. So here I'm taking the case of a flow or a flat plate. This is just a first, similar to my first question. So I have a flow or a flat plate. So thermal conductivity of solid is given case, thermal conductivity of fluid is given. So first I write the expression as minus k dt by dy at y is equal to 0 by t minus ts minus t infinity. So we have a velocity boundary, thermal boundary layer. Okay, and we have a this is ts and t infinity. So I'm asking whether this k is k of solid or k of fluid. That is my question. So which k should be used? Okay, I mean, is the k of the solid or k of the fluid? Actually, just think about how we derive this expression. That is it. So here we have the first layer of molecules which are stagnant, right? So whatever heat that is transferred from this plate to the fluid, so it will transfer to the first layer of fluid by conduction because this is stagnant, right? From that stagnant layer of molecules or fluid layer, it is convected to the free state. So it is minus k fluid dt divided by dy at y is equal to 0. So this temperature profile should be is the temperature profile of the boundary layer. That also you should be very careful. So the temperature profile of which section it is given. So it is minus kf dt divided by dy at y is equal to 0 is h ts minus t infinity. So from this expression only we find out h value. So normally what people will do is okay, this is h, and from h only we are getting what Nusselt number is h d by k. Okay, so the Nusselt number in Nusselt number expression and also in the heat transfer coefficient expression, which is derived in this way, the thermal conductivity of the fluid is used. I hope you remember a similar kind of questions, similar kind of expression we discussed in the previous classes. That is in the transient conduction case. That is lumped analysis. If we use Biot number, that is HLC by K. Here, so normally people will get confused between this. So here it should be K of solid should be used because in Biot number, we are checking whether the temperature distribution within the solid is isothermal or we are our concern is the conduction resistance to the convection resistance. It is a comparison between the conduction resistance within the solid to the convection resistance. So the conduction resistance should be very less within the solid. Conduction resistance should be very less within the solid so that the body we can approximate as an isothermal body. Right. So here in Biot number, we should be using, you should use the thermal conductivity of solid, not fluid. So please don't get confused because in some questions you will get both. They will give both the thermal conductivity of solid and also fluid. So you should take the appropriate value. In case of Biot number, you have to consider the thermal conductivity of solid, and in terms of and in for Nusselt number expression, you should take the thermal conductivity of fluid. So this is a false statement. So okay. Uh, so sorry, this sixth question I did it completely. So this depends on the type of flow. So Prandtl number is actually a, sorry, I'm jumping back. I will first finish this question. So this I hope this is clear. This Nusselt number, the thermal conductivity should be used. It is what we should use thermal conductivity of fluid. So in this Prandtl number, I'm going back to the previous question. So in Prandtl number is a fluid property. It's a fluid property. It does not depends upon the type of flow or the geometry. Okay. So it's a property of a fluid, just like thermal conductivity, viscosity, specific heat, like that. The Prandtl number is a property of fluid. It does not depend upon the type of flow or the nature of flow. Okay, but heat transfer coefficient depends upon the will depend upon fluid properties, type of flow, and nature of flow. But Prandtl number is a fluid property, so it doesn't depends upon the type of flow. So the answer to this question is false. The Prandtl number does not depends upon type of flow, but it can a function of temperature. Okay. So we will go to the last question. So consider a flow over a flat plate where the temperature of the fluid and plate are different. Heat transfer at the leading edge will be less than the trailing edge. So this is the leading edge. This is the trailing edge. Okay, so I am considering this that for the entire length of the plate, the flow is lambda. Okay, so this is the boundary layer, means thermal boundary layer. It is. So I am taking two points. One is here, and one is this plate. So these are the means these are the temperature profiles. Okay. So if you see near to the trailing edge, sorry, at the leading edge, what you will see, the temperature is increasing from Ts. I'm considering Ts greater than T infinity is increasing or decreasing. So the Ts is decreasing from, so the temperature within the boundary layer is decreasing from Ts to T infinity with a very short distance, which means at this area, dt by dy is less as compared to, sorry, more, because the gradient, the temperature, there will be we'll call it as a sharp gradient. That is, the temperature is changing within a very short, changing from Ts to T infinity within a short period of time. So there is a sharp gradient near the leading edge than the trailing edge. In the trailing edge, as we know, the boundary layer is growing from the leading edge to the trailing edge. So here the temperature gradient at the trailing edge will be what? It will be less as compared to the temperature gradient at the leading edge. We already given that the heat transfer coefficient is defined as Ts minus T infinity. Okay. So here Kf, Ts, T infinity all are same. So H is proportional to the temperature gradient. So as the temperature gradient at the leading edge is greater than the temperature gradient within the boundary layer at the trailing edge, the heat transfer at the leading edge will be higher than the heat transfer at the trailing edge. So this will means what is the expression means what is the expression for heat transfer coefficient with respect to x, and all you will study, we will derive. I hope we will derive in the coming lectures. So that time you will get more clarity on this concept. So just now I am just linking it with the temperature gradient. So we will derive the exact expression, means h as a function of x and all. We will derive in the coming sessions. Or we will be studying, or you can refer to any heat transfer textbooks like in Fokker or Stengel's, the convection portion. There it is derived. Okay. So so we come to the end of this session. So thanks for listening, and have a nice week ahead. So see you next Monday. Thank you.